So far, all of the integrals that we've done have been not too complicated. However, I'm going to show you what to do in some cases when you get more complicated integrals. So here's an example. You don't need to write it down. We're going to go over it in just a few minutes, but I just want you to take a look at this. So if you have something like 2x times x squared plus 1 to the fourth power, this type of thing, the only way you know of right now to integrate it is by multiplying x squared plus 1 out 4 times and then multiplying it by 2x. If you did that, there'd be a high probability that you'd make a mistake in there somewhere just because it's such a long, complicated process to do. So rather than writing out a complicated product, we are going to use something called substitution. And substitution is, I kind of think of it like the reverse of the chain rule. It's almost like the chain rule for integrals. So like if you were to look at this original function, you might notice that the inside of the function, if you were to take that derivative of that, you would get 2x. So the antiderivative is going to be using the chain rule backwards. And we do what's called substitution. That's used to integrate a function whose derivative involves the chain rule. What you're going to be looking for is a function whose derivative matches up with another part of the function. So the function whose derivative matches up with another part of the function is going to be, you can call it your u function. Basically, we're going to set that equal to what we call a dummy variable, and we'll call it u usually. So that's why it's called substitution. Once you do that, I'm just kind of giving you the steps, and then we'll go through an example or two. Then you will simplify to get something you already know how to deal with. So we're going to simplify to get something we already know how to integrate. And let's do a few examples. So I'm going to start with that example I have at the top. So we are going to integrate 2x times x squared plus 1 to the fourth dx. And what we're going to do is, you'll notice that if you take the derivative of x squared plus 1, you get 2x. So that x squared plus 1 is going to be our u function. So what I'm going to do is I'm going to set u equal to x squared plus 1. Then I am going to take the derivative of that. So when I take the derivative of that, I'm taking the derivative of u with respect to x. That's going to give me 2x. And I generally don't write this step that I just wrote. I usually just write it as du is equal to 2x times dx. I kind of broke up that du and the dx. Once I have that, I can divide both sides by 2x. And this is looking really weird right now. You probably would, I'm imagining. So then you get dx is equal to du over 2x. So now you're probably looking at this wondering what we're going to do with all of this strange stuff. So what we're going to do is we are now going to change this integral so that it is no longer in terms of x, but it is now in terms of u. And so what I'm going to do is I'm going to keep my 2x there. However, this x squared plus 1 is now going to change to u. The other thing is that I have a dx right here to show that I'm not going to be differentiating or not integrating with respect to x, but I'm doing it with respect to u. I'm going to replace that dx with this du over 2x that I got before. And if everything works out correctly, which hopefully it will, you should get something that cancels out all your x's. This one's even nicer because my 2's also cancel out. So now my new equation becomes the integral of u to the fourth du. Okay, so now we're going to take that integral. You're going to do the antiderivative of u to the fourth, and the antiderivative of u to the fourth is u to the fifth over 5. Don't forget your plus c. The last thing that you need to do is rewrite that u as what we started with. We're going to back substitute. So we're going to substitute x squared plus 1 back into that original equation. We want to end with the variable that we started with. So then this right here will be my answer. It's a good habit to get into to check your answers for any integrals that you do, especially if they're really complicated. So my answer was 1/5 times x squared plus 1 to the fifth. I wrote it with the 1/5. I think it's easier to look at. You could keep it as over 5. So I'm going to check by taking the derivative. And hopefully, if you did everything right, hopefully you'll get back to what you had in the original problem. So when I take the derivative, I'm going to do the chain rule. And so you, first of all, take the derivative of the outside part. That means you bring that 5 out front. So I get 5 times 1/5. Keep the inside the same and subtract 1 from the exponent. Then you multiply by the derivative of the inside, which is 2x. The derivative of c is 0, so that goes away. And you end up getting 2x times x squared plus 1 to the fourth. You got the same thing that you started with, which is good. That's what we want. So if you're feeling like you might understand this, go ahead and try this one. Okay, so we're going to, I want you to notice that if you take the derivative of x cubed plus 1, you do get 3x squared. So I'm going to do u equals x cubed plus 1. Then if I take the derivative of both sides of this, I get du is equal to 3x squared dx. You'll notice I skipped the intermediate step that I had done in the last one, the du over dx. Then if I divide both sides by 3x squared, I get dx is equal to du over 3x squared. So now I can go back to my original equation. I keep the 3x squared the same. I can't do anything with that yet. I am going to now take this stuff inside of the square root and replace it with u. I am going to take this dx and replace it with this stuff right here. Now the 3x squareds are going to cancel out, which is good. We can't really do the problem if they don't. And I'm just going to be left with u to the 1/2 du. Now you can just take the derivative of that one. You get u to the 3/2. Actually, you get 2/3 u to the 3/2 plus c. The final thing that you need to do is plug in your original u. And I do recommend that you go back and check your answer by taking the derivative. I'm not going to do that right now, but you certainly can do that on your own. So we're going to do one more like this, and then I want to do some that are definite integrals. You're welcome to pause and try it on your own, by the way. So for this one, we are going to, I do want you to notice that I have my u, really there's only one option for it. It's going to be 2x plus 1. I actually don't have anything, I don't have a derivative or anything that's going to cancel out. However, if you have a constant, the constant isn't going to, it's not going to affect the integral itself. It's just going to be there in the end. So now I'm going to take the derivative of this u. I get 2 times dx, which gives me dx is equal to du over 2. And I'm going to go ahead and rewrite this as u to the 1/2, or you can say square root of u if you want to do the next step. This dx is replaced with du over 2. And actually, that 2 is a constant, so I can pull that out front. Just notice that it's at the bottom of the fraction, so it's got to stay at the bottom of the fraction. So I end up getting 1/2 u to the 1/2 du. Now I'm just going to use what I know about taking the integral of a power. So I'm going to add 1 to that power, and then it's going to be multiplied by 2/3. And also, don't forget the plus c. Last step is to simplify and replace your 2x plus 1 in for your u. So here's another one, and it looks like you actually can't solve it using substitution, but believe it or not, you can. So if you get something like this, you might notice that if I do a u, I'm actually going to get nothing that cancels out when I do the du part, but there's a little trick involved in this type of problem. So first thing I'm going to do, I have a function under my square root. I need to get rid of that and make it a little bit easier to deal with. When I do that, I get, so I get u equals x plus 3, and I get du equals dx. Now, I have an x there. I have a square root of u there, and I also am going to rewrite my dx as du. The nice thing about this one is I at least didn't have any constants left over. But the thing about this problem that looks weird is that I now have an x and a u in my equation. It looks like I can't do anything, but actually, believe it or not, I can. There is one more thing I can do. I can take this u and I can rewrite it. I can solve it for x. So if I subtract 3 from both sides, this can be rewritten as x equals u minus 3. Now you might be thinking that how does that change anything? Actually, it changes it a lot. It makes the problem solvable now. So when I do this, I now am going to replace this x with u minus 3. I'm going to change this square root of u to u to the 1/2. Now suddenly the problem is similar to things that you've seen in the past. The only thing you need to do now is distribute and then do the integral. So when I distribute this, I get u to the 3/2 minus 3 u to the 1/2. This is now something I'm able to solve. When you do that, you end up getting 2/5 u to the 5/2 minus 3 times 2/3 u to the 3/2 plus c. So then we can go ahead and plug x plus 3 back in for u. So my final answer, my 3's cancel out, which is nice. Final answer is going to be this right here. Another one, you're welcome to take the derivative of this to see what to make sure you get what you started with. You will get what you started with. You might have to do a bunch of simplification, but it does actually work out. We're going to do a definite integral. And the thing about definite integrals that tend to get confusing is that you're dealing with both x values and u values. So the first thing I want you to notice is that this thing right here inside of the parentheses is going to be my u. I get u equals x squared plus 1. That gives me du is equal to 2x dx. If I divide both sides by 2x, I get that dx is equal to du over 2x. So I'm going to go and substitute back into my original equation. And the one thing I want you to be careful of once you have substituted stuff in is I want you to remember that these values right here are x values. So I personally like to do this problem by just writing out x equals 0 and x equals 1. I think that's helpful when you're doing this type of thing so you don't get mixed up and try to plug those into a u. So let's go ahead and work out the u part of this, the u substitution of this problem. We get x times u to the 3rd. The dx is going to be replaced with du over 2x. Remember that 2 can be pulled in front as a 1/2. The x's inside are going to cancel out. Then I'm going to be left with x equals 0 and x equals 1 as my constraints. I have u cubed times du. Now, we're going to go ahead and work this out. We get u to the 4th over 4. Now, keep in mind, these are x values. Please do not plug them into the u that you have. If you plug them into the u, you're going to get the wrong answer. So you must change the u back to something in terms of x's before you actually do any of the substituting back in. Okay, so the 1/2 times u to the 4th over 4 ends up being u to the 8th over, or u to the 4th over 8. But I'm actually going to write that as x squared plus 1 to the 4th over 8. I'll just bring the 1/8 out front. I think that makes it easier. That goes from x equals 0 to x equals 1. You can keep the x equals in there if you want to. So when I work that out, I get 1/8 times 2 to the 4th, that's what happens when I plug in 1, minus 1/8 times 1 to the 4th, that's what happens when I plug in 0. So I end up with 16/8 minus 1/8, which gives me 15/8. So this is method 1 of doing this problem. It might have been long, but actually this is the easier way. In my opinion, it's easier. Now, that being said, you will be required to recognize something a little bit different. And I'm going to go back to the part of the problem right here. So starting as soon as I figured out my u substitution, so method 2. I'm just going to do it right below all of my u stuff. So for method 2, you need to change the limits of integration. And I'll show you what I mean. So you probably noticed that for all of method 1, I was writing out like x equals 0, x equals 1. Now, you don't need to keep them as x's. In fact, you might find it easier to figure out what your limits of integration are in terms of u. So my lower limit was x equals 0. You can actually figure out that that is equivalent to u equals 0 squared plus 1, which is 1. My upper limit was x equals 1. That is actually equivalent to u equals 2. So we can rewrite this equation as u equals 1 to u equals 2. And now I'm going to go back to what I got right here. After I did all this substitution, I got 1/2 times that integral, u to the 3rd du. I want you to keep in mind that if you see anything with a u substitution and there is no variable listed with the limits of integration, which it's usually not going to give you that it means that they are in terms of u. I think that these get really confusing for people. It appears often on a multiple choice question. It's up to you though if you want to do method 1 or method 2 when we're doing this together in class. So I end up getting 1/2 times u to the 4th over 4. This should look pretty familiar. This time, however, I am not going to substitute my original equation back in for you. I am just going to, do u to the 4th over 8 and then evaluate it at these two values. So when I do that, I end up getting 16 over 8 minus 1 over 8. And I did get the same answer, 15 over 8. Now, if you found this method easier, that's great. I would use it every time. If you found the first method easier, feel free to use that. Just make sure that you label it and you remember that you're using x values. However, the second method you will see on the AP exam. So use which one works best for you. You'll get the same answer in the end.